All right, so this is our last bit of chapter 16. We're going to deal more with Gibbs energy. In this lesson, we will define Gibbs energy and describe how it relates to spontaneity. We'll calculate Gibbs energy change using Gibbs energy of formation for reactants and products. And we'll calculate the Gibbs energy change using standard enthalpy and entropy of formation for reactants and products. Your book titles this section of the chapter Free Energy. And it also calls it Gibbs free energy within the chapter. Some books will refer to this as Gibbs energy. All of these terms can be used interchangeably for the same concept. Gibbs energy is defined as the change in Gibbs energy is equal to the change in enthalpy minus temperature in Kelvin times the change in entropy. But what in the world is Gibbs energy really? If you use the conservation of entropy equation from the entropy definition slides, and you use a bunch of substitutions, and I do mean a bunch, you can derive that Gibbs energy is equal to negative T times change of entropy of the universe. You do not need to see the full derivation of that. We will save that for if you take physical chemistry. Instead, what we are concerned with is what is spontaneous versus non-spontaneous. So if our entropy of the universe is less than 0, in other words, the system is getting more ordered, then our delta G will be positive. That is not spontaneous. For increasing entropy, that's not spontaneous. What about if entropy is in fact decreasing? So we have entropy increasing, then our delta G is negative. That is spontaneous. That is going to happen. And finally, if delta S of the universe is equal to 0, then we are at equilibrium. Both the forward and the reverse reactions are going to happen spontaneously. So on your phase diagram, the line represents where dg is equal to 0. We have discovered something new, and we've applied it to something old. So the reason why your book calls it the Gibbs free energy is that when the Gibbs energy is negative, it represents the maximum amount of work that you can do with that given system. So delta G is then equal to W max. But, and this is the reason why I prefer to call it just Gibbs energy, not Gibbs free energy, when the Gibbs energy is positive, it represents the minimum amount of work you need to do to make that change occur. So delta G will equal to W minimum when Gibbs energy is positive. Okay, so to keep it straight, I think of it as just Gibbs energy. You guys can think of it however you would like. Your book will continue to call it Gibbs free energy. Now, conveniently, Gibbs energy is a state function. So the standard Gibbs energy is for creating 1 mole at 1 bar from the elements in their standard states at 25 degrees Celsius or whatever temperature you're using, because the temperature will depend on the reference that you have. It turns out that there are a bunch of standard Gibbs energies for like biological systems, which will actually be at 37 degrees. Moving on. You can use the standard enthalpy and entropy to calculate standard Gibbs energy. So delta G standard is equal to delta H standard minus T delta S standard. Additionally, you could look up the Gibbs energy in table G1 and just do it the way that we have been doing it, which is the products minus reactants. Both are perfectly valid, and we're about to see why. All right, so let's try the calculation using delta H and delta S values from the book. Calculate the standard Gibbs energy for the following transition using the standard enthalpy and entropy at 25 degrees Celsius and determine if this change is spontaneous. So I looked up the values in the book, so they're given here, and it was in Appendix G, in case you're wondering. The change in enthalpy and the change in entropy are found by taking the final state minus the initial state. So let's do that. Here we go. 58.91 minus 0 is 58.91. 280 minus 164.4 is 115.6. So at this point, we're going to use the Gibbs energy equation. We have our delta H, we have our delta S. What is our temperature? 273 plus 25 is 298. So that's our temperature in Kelvin. We're going to plug all those things into the delta G equation. All right, so when I plugged in these values, I made entropy and enthalpy into the same unit. Look carefully. Enthalpy is in kilojoules per mole. Entropy is in joules per Kelvin mole. So the Kelvin will cancel because we're multiplying by temperature, but the kilojoules and the joules are different units. So I converted my entropy into kilojoules per Kelvin mole, and I multiplied it by my temperature in Kelvin in order to make this work. So make your units match, or you will definitely get the wrong values. This particular value, once I plugged everything into my calculator, was positive 24.3. So at room temperature, this change is non-spontaneous. Phosphorus will not go from solid to gas. That checks out with my lived experience. I have never seen phosphorus gas just floating around at room temp. Okay, so let's try it the other way. In this case, we're just going to look up the Gibbs energy values from the book at the table. And we have our Gibbs energy gas and our Gibbs energy for solid, which was 0, because that's its standard state at 25 degrees Celsius. And we just do final minus initial. We get 24.4. Again, it's not spontaneous, still agrees. 24.4 and 24.3 are different by 0.1. Within error, this is the same result. This is a rounding error at the very end. We're fine. It doesn't matter whether you use delta H and delta S from the table or delta G, they'll be the same numbers as long as you do your process correctly. All right, so let's try to extend this to coupled reactions. So if you remember, thermochemical equations have a thermodynamic property at the end. In this case, we'll be doing it with Gibbs energy, but you've done it with enthalpy before, and we could do it with entropy. It's always the same basic rules. Number 1, if you add equations together, add up the Gibbs energy. If you flip an equation, flip the sign of the Gibbs energy, or the enthalpy or the entropy, whatever, flip it. If you multiply or divide by a coefficient, include all reactants and products and thermochemical values. So if I were to divide everything by 2, I would also divide the Gibbs energy by 2. So let's try an example of this. What is the Gibbs energy of the following coupled reactions? So we're going to take these two and we're going to add them together. Reactant side to reactant side, product side to product side. Okay, and we get calcium carbonate solid plus carbon solid plus oxygen becomes calcium oxide and CO2. Now we also want to add together the delta G's. So 134.4 plus negative 394.36, which is basically the same as saying 134.4 minus 394.36. And we get negative 263.96 kilojoules for that coupled reaction. This is not actually foreign. You have done this stuff before as a Hess's law problem with enthalpy. We're just extending this idea to Gibbs energy. Gibbs energy, delta G, is equal to the change in enthalpy minus the temperature in Kelvin times the entropy. When Gibbs energy is negative, the system is spontaneous, and it will indicate the maximum amount of work that system can do. When Gibbs energy is positive, the change is non-spontaneous, and it indicates the minimum amount of work you have to do in order to make that change happen. You can calculate standard Gibbs energy from standard enthalpy and entropy, or you can just look up standard Gibbs energy in the table, and that works too. And finally, when we're manipulating thermochemical equations, which are equations that have a thermodynamic property at the end, if you add the equations together, add the Gibbs energy. If you flip the equation, flip the sign of the Gibbs energy. If you multiply or divide by a coefficient, include all reactants, products, and the thermochemical value when you do that. All right, that is a summary of all the Gibbs energy definitions. Well, the definition of Gibbs energy.